All right. One of the most useful applications of antiderivatives is in analyzing the motion of an object moving in a straight line. We recalled in a previous lesson that the derivative of position is velocity, and the derivative of velocity is acceleration. Going in the opposite order, that means that the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. Thus, one could determine the position function by antidifferentiating the acceleration twice. The only problem with doing this is those arbitrary constants that we get, c and d, when we antidifferentiate twice. But if we know the initial position and we know the initial velocity, we can use those data points to plug in and determine the values of those constants and figure out the exact position function. Let me show you what that looks like, because that was a lot of words, and I think it's probably better if we look at an example. So I'm going to write down this example now. I'm going to pause the video so you don't have to listen to me as I write everything slowly. All right. A particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6, and its initial position is s of 0 equals 6. Find its position function, s of t. Okay, we're given the acceleration function, and we know that the acceleration is the derivative of velocity. So that means if we want to find the velocity, we have to take the antiderivative. So let's figure that out. The velocity is going to be the antiderivative of acceleration. Well, the antiderivative is 6t. If we antidifferentiate t, that's t squared over 2. And we've got that 6 there, so we've got to take the 6 and put it over 2. 6 divided by 2 is 3. So that's going to give us 3t squared plus 4t, because the antiderivative of a constant is equal to the constant times the variable. And then plus a constant term, which we'll call c. But remember, we know something about the velocity. We know the initial velocity is negative 6. So v of 0, which if we plug in 0 for t, that's going to be 0 plus c. We know that that's negative 6, so that tells us that c is negative 6. And so we actually know the velocity function is 3t squared plus 4t minus 6. We can use that information we knew about the initial velocity and narrow down what the constant term is, so we can have an explicit formula or a specific formula for the velocity here instead of a generic one with a constant term in it. Okay, now that we have the velocity, if we want to find the position function, we're going to have to antidifferentiate again. So let's do that. The antiderivative of t squared is t cubed over 3, but taking that 3 and putting it over 3, the 3's cancel. So we just have t squared plus the antiderivative of t is t squared over 2. And so we've got that t squared. And if we take the 4 and put it over 2, that gives us 2. And then minus 6t, because the antiderivative of a constant is that constant times the variable. And then plus we need our constant term. I'm going to use d, because we already used c in this problem. So that is our position function, but we don't know it exactly because we've got that constant in it. However, we do know that the initial position, or the position at time 0, is equal to 6. So we know that if we plug in 0 for t, which makes a bunch of these terms 0, that just gives us d, and we know that that's 6. So that gives us the value of d, and plugging that in, we know that our position function is going to be t cubed plus 2t squared minus 6t plus 6. And so we know our exact position function, and we should always be able to do that so long as we have the acceleration function and we've got one piece of information about the velocity and one piece of information about the position. Having those pieces of information, that is enough to solve these sorts of problems and figure out the exact position function. Now, before you look into some of the example problems that you're going to see videos of, and then homework problems, I do want to talk about one particular thing, and that is acceleration due to gravity. One really great example of these sorts of problems where we start with the acceleration and we work backwards to find the velocity and position functions deals with projectile motion. That is the sort of motion that an object would have if you threw it up in the air and let it go, and the only force acting on it ends up being gravity. So if you were to throw a tennis ball or a football or any sort of ball in the air, or even a pencil or whatever, that is projectile motion. And when something is moving through the air, like a projectile, the only acceleration that's happening is the acceleration due to gravity, and that is a constant. So long as we are close to the surface of the Earth, that acceleration is given by g, a constant, and that is approximately equal to 9.8 meters per second squared if we're dealing with metric, or 32 feet per second squared if we're dealing with imperial units. These are two numbers that wouldn't hurt to memorize, and these are going to show up in a couple of the example problems where we're dealing with projectile motion. In those problems, acceleration is going to be constant, and it's going to be 9.8 meters per second squared, or 32 feet per second squared, depending on if we're using metric or imperial. So you'll see that in just a little bit.